see, guys, we're getting into this last unit I want to cover. It doesn't cover a full chapter, but we're going to wrap up chapter 5, this whole idea of integration. And then we'll do the first part of chapter 6, which will entail applications of integration. Okay, so say we get the substitution rule. Just to make sure that you're on the right page with me, go ahead and integrate this indefinite interval. Go ahead and hit pause on the video. I'll work it out while you work it out. All right, did you even hit pause? If you did, you probably found where you could not work it out. If we don't have rules for this. This violated our integration rules that we talked about so far. I'm not sure what I'm taking the derivative of in order to get to this point right here. And so we're going to need a little bit of help, and that's where this substitution rule comes in. Okay, so formally introduce the substitution rule. It says if you got u equals g of x, and that's a differentiable function whose range is on an interval and f is continuous on I, then what we can conclude is that the interval of f of g of x, okay, so we're going to have that composite function right there, times the derivative of g, the inside, dx, can simply be written as the integral of f of u du. That makes it look a lot harder than what it actually is. So let's actually plug in some numbers, okay? So I want to find this indefinite integral. So the first order of business is going to be do my substitution. You're going to hear me refer to it as a lot as a u substitution, as that's exactly what it is. And so my u substitution, my u is going to be whatever is on the inside of the function. When we talk about a composite function, we have inside and outside. My u is going to be what's on the inside of the function. So what's maybe inside parentheses, inside a denominator, inside a square root, in this case inside a cosine. That's a good starting spot. Now, will it always be that? Absolutely not. Sometimes you're going to have to erase it, and you're going to have to try something else for you. Just get used to that. Okay. Now, from here, I'm going to get my, as you can see, I've got stuff in terms of u right here, and then this is dx. So I'm going to need to get everything to kind of agree. So I'm going to take the derivative of both sides. So I'm going to take the derivative of u with respect to x, and that gives me 4x cubed. Okay. Now normally I'm going to do all this in one step. I'm going to go ahead and move this dx, multiply both sides by dx, and you'll see why that's needed in just a minute. Now as you can see, I'm starting to match this little guy that's out here in front, except for I've got this 4 in the way right here. So what you're going to hear me say is that I don't really need this 4, so what I'm going to do is I'm going to do algebra, divide both sides by 4, or multiply both sides by 1/4, either way, and I am going to get 1/4 du is equal to x cubed dx. All right, now that we've done all that, let's see what my new integral looks like. Well, the x cubed and the dx, they're going to go away with the 1/4 and the du. So 1/4 and the du. That's my substitution step. Okay. I still have the cosine. I'm just going to bring it over. But instead of taking cosine of x to the 4th plus 2, remember that's what my u is equal to. So I've successfully changed my whole integral into something that looks pretty messy with the original problem right here, into something that looks a lot easier. And that's what I want to do. I just want to integrate this. So remember that 1/4 can come out in front. If you want to pull that 1/4 out in front, that's where you're going to see me put it most of the time. And so Yeah, I'm just taking the integral of cosine of u. And so if I integrate cosine u, the antiderivative of it is going to be simply sine of u. Plus c, because we are on the indefinite integral. Now, my original problem was in x, so I want to end my problem in terms of x. So this u substitution is going to come straight back down, and I'm going to have x to the fourth plus 2. And this would be my answer. If you don't believe me, you can definitely take the derivative of this. If I take the derivative of this, I've got 1/4 derivative of sine is cosine x to the fourth plus 2. It's just a chain rule times the derivative of the inside. The 4 and the 1/4 cancel. Look what I'm left with. Cosine of this times x cubed, which is exactly what I started with up here at the top. Okay, so it does work, and it's an easy check on all these. Okay, let's do another one together. We'll be pausing the video some and letting you work some on your own and trying to match up to where I end up with. So let's try this again. Hopefully you can kind of figure out what the u is going to be. U is going to be 2x plus 1. Okay, automatically I know I'm going to need a du. I want everything in terms of du. So I tend to do my steps all in one right there. So I go ahead and multiply both sides by dx when I take the derivative. So I get du is equal to 2 dx. Next question is, do I need this 2 with my substitution? Well, I'm looking up here. There's not a 2 floating around anywhere outside of my integral, or inside my integral, or outside for that matter. And so yeah, I'm going to go ahead and divide off that 2 because I, quote, don't need it. And again, that's going to allow me to go ahead and rewrite my integral to something that looks a lot easier. And so I'm going to put that 1/2 out here in front this time, just to keep it out of the way. And then the 1/2 and the du will take place of this dx. And all I'm left with is the square root of that function. Well, remember, that function is what I'll let u equal. So if I integrate, let's see, this, if you need to, you can write this as u to the 1/2. And so if I integrate u to the 1/2, take the antiderivative of it, I need to raise the exponent by 1. That would be u to the 3/2. And then put it over the new exponent. Dividing by 3/2 would be the same as multiplying by 2/3. Then you get the plus c. 2's cancel. You're left with 1/3. And then your u is 2x plus 1. Raise that to the 3/2. And you get plus c. So we are able to integrate a little bit harder of a function now thanks to this u substitution. Okay, I'll get you started on this one, then I'm going to turn you loose on the second half. Again, this is, I just know what to plug in for you, maybe because I've done this so much, or I'm just looking at what's on the inside. And so my u would equal 1 minus 4x squared. So that means that my du over dx, and we'll multiply both sides by dx, would be negative 8x. So looking at that, what do I need? What's outside of my cell? I could use an x. I really don't need this negative 8. So I'm going to divide off the negative 8. And that's going to equal x dx. That should help me with my substitution. Because so now I can rewrite this integral a lot easier. I have my negative 1/8 du. That's going to take the place of this x and this dx. So all I'm left with is 1 over the square root of this whole function, which I substituted for you. All right, you guys wrap that up, and I'll do the same, and then we'll see if we match answers. Just go ahead and hit pause on the video. Okay, that's what I got. If you didn't get that, pause it, kind of look and see what I did, and then you can join us back up whenever you get that right answer. All right. I told you we're going to be pausing the video a lot. I'm just letting you guys have this one. All right. Shall I let you guys have it? Yeah, I think I should. This would be a good one for you. I'll get you started with your U on this one. Hopefully you can kind of see what the U is. Look, don't ever say that U is equal to the whole thing. That defeats the whole purpose of the U substitution, because then we're just going to plug it all back in. And so let U be what's on the inside. In this case, the inside of your exponent. Okay. Now hit pause. You work the problem, and I'll do the same. And there it is. Because I really don't have a lot more on this. It's just going to be a lot of examples. So I think the more of these we see, the better off we'll be. So probably asking yourself, how can my bald math teacher with big teeth make this any harder? I didn't make it harder, right? But it does get harder. Right? So we can do this one. We can come back together on this one, and I'll turn you loose on the next one. All right, so just looking at this, U is equal to, has to be what's inside right there, 1 plus x squared. That's the only thing that really makes sense. So I've got this x to the 5th hanging out right here, so I'm going to have to deal with it in just a little bit. So my du is going to equal 2x dx. Okay, so I'm looking at it. Do I need the 2? I don't need the 2. Looking at it, do I need the x? Well, I actually need 5 of them. Well, four's a pretty good, or 1's a pretty good start right there. So I'll leave the 1 x over there. Oops, brought the 2 over. Now I made it to here. Does that help me any? Well, I'm able to rewrite my integral now as, let's see. I don't want to rewrite the whole thing. I'm going to leave it in terms of x. So maybe rewrite it as 1 plus x squared. I've got this x taken care of, but I still have 4 more x's there to play with. So I didn't want to put in my u's yet, because I really want to avoid having u's and x's in the same integral if I can. I want it, whenever I'm ready to move everything to u's, I'm going to do it all at once. So if I could just, so I know that this x and dx is going to be taken care of by the 1/2 in the du. Okay, so whenever I rewrite this one more time, should have left myself more space, the 1/2 du will take care of the x and the dx. And I have this square root of u happening right here. That's going to take care of all of this. So I just have this x to the 4th. I don't want to bring over the x to the 4th because everything's in terms of u, and I like that. This is where I look at you guys and say, any ideas? But my room is empty right now, so you don't have any ideas. You're just probably just going to sit there and wait for me to tell you. Here's the kicker on this one. And this one doesn't happen very often at all. Okay, I've seen it on the CMO final though a couple times. I look back, and the closest thing I had to that x to the 4th, I have this x squared right here. Right? If I have that x squared right there, if I solve for it, I get x squared. I'm gonna subtract the 1 over. It equals u minus 1. That's good, Mr. Lovelady, except for we have 4 x's right there. So, okay, all right. I'm just going to square both sides. And that gives me my 4 x's. In terms of u, so I can bring this guy over as u minus 1 squared. Now, we have some algebra to do on this before we start integrating. Okay, so I got my 1/2 hanging out in front. I'm trying to leave myself more room while still being able to flow on the board. Let's see, I got my 1/2 hanging out in front, and then I'm going to need to expand this. I'm going to go ahead and call this u to the 1/2, because if that square root's not going to do me any favors. If I expand that u minus 1, and make it to here, well, that's good, but still, I can't just integrate this and integrate this. I didn't have a rule for that. All right, there's not an anti-product rule just yet for undoing a product or however you would want to think of this. I want it as just something that was on one of those tables that we had in a previous chapter or a previous section, or just something recognizable, or as that I call it a pseudo-polynomial form where everything is just being added and subtracted from each other. Well, good news. All I gotta do is just distribute this, and I'll get u. So whenever I multiply these, I add their exponents. So 2 plus 1/2 is 2.5. If I put it as 5/2. Minus 2, see 1/2 and 1 is 1.5, or 3/2. And anything multiplied by itself is just 1. Now I have something I can integrate. Okay, so I have 1/2. Let's see, raise the exponent by 1. That would be u to the 7/2. Put it over the new exponent. Put it over 7/2, the same as multiplying it by 2/7. Minus let's see, I raised the exponent by 1, u to the 5/2. Still got the 2 out here in front. Dividing it by 5/2 is the same as multiplying it by 2/5. Sorry, I kind of ran together right there, but I'll fix it in there. Raise the exponent by 1, put it over the new exponent, or multiply by its percent. Plus c. So I'm going to kind of do several things on this last step right here, because I'm ready to get off this problem. 1/2 times 2/7. I'm going to distribute the 1/2 through. So 1/2 times 2/7, that gives me 1/7. And then I'm going to plug my u back in. Remember the u way back over here? 1 plus x squared? Yeah, it's coming back. Minus. Well, that's going to give me 4/5. 4/5. Half of that's 2/5. So, or you could just have the 2 and the 1/2 cancel. That would work as well. So 2/5, 1 plus x squared to the 5/2. Plus, say half of 2/3 is 1/3. Oh, I didn't leave myself nearly enough. 1 plus x squared. 1 plus x to the 3/2. Oh, the square goes in here. Here we go. So 3/2 plus c. This guy right there. That is your answer. Whew. I could have fun and expand all that out, but we'll just leave the answer like that, and I'm sure that the book will too. All right, you're on your own on this one. Might be looking at it and saying, hey, there's no inside function. We just have to make one. Maybe we should rewrite this tangent. How do we rewrite tangent? Sine over cosine. So I'll let you play with this one. Hit pause on the video. I'll work it out, and I'll meet back up with you. All right, this is one possible answer. I don't think this year on this video I'm going to worry about the other possible answer, but this one will be fine. Okay? Now, one about you might have forgot these absolute value signs. We have talked about why we need these absolute value signs, but anytime I have 1 over u and I'm going to integrate it, I need to have the natural log of the absolute value of x. I proved that previous this year, and so if you have questions on that, put a big star by it, and I'll be glad to do it again during our Q&A. All right, well, we did all these indefinite integrals. How do we tackle this with definite intervals? Because we're switching variables. We're going from x's to u's. So do I have to go back to x's, or can I leave it in u's and plug it in? All great questions. Okay, so let's have it make sense to us. Now, this is a problem that we have already done. The square root of 2x plus 1, I thought we already did it. Yes, I think it was like example 3 maybe. I'm not sure. But whenever we work this out, we worked it all the way down. I'm just going to kind of cut to the chase. I'll just say previous example. Okay? And so whenever we worked it all the way out, all right, we got all our work, and we got it down to 1/3 u to the 3/2 plus c. And so what we did was we took that u, we said our u substitution was this 2x plus 1. Hopefully you have that in your notes. So I just don't want to rework the whole thing. I think that would be a waste of time. To the 3/2. But this time instead of the plus c, we know what we want to integrate from. We want to integrate it from 0 to 4. So I can, if it's a definite integral, I can rework the whole problem the same way we have been doing, and then whenever I get to the end, I can plug in my upper limit of integration. So if I plug in 4 in for all of this, let's see, let me do this kind of in my head here. So 4 times 2 is 8, plus 1 is 9, square root and, oh, let's do that. I'll just do 9 for now. Okay. And if I plug in 0 in for all this, unfortunately it doesn't go to 0 because I got 0 plus 1 right there. So it's 1/3 times 1 to the 3/2. Well, anything raised, 1 raised to any power that's finite is going to be 1. So all this just goes to 1/3. And here, again, your calculator will do all this. It's good to do this mental math, though, to keep you bright or keep you sharp on some stuff. Square root of 9 is 3. 3 cubes, 27. 1/3 of that is going to be 9. So I can actually go ahead and find the area that would be under this curve between 0 and 4. It would be 8 2/3. So that way is not bad, but I'm here to tell you that there's another way. You don't necessarily have to go back to the x's. And so let me show you that way. It says if g prime is continuous on the closed interval AB and f is continuous on the range of whatever g of x is, which is going to be what we plug in for our u substitution, then the integral from a to b of f of g of x times g prime dx is going to equal, this is going to be kind of weird, g of a and g of b f of u dv. So as you can see, you and my friend sitting together. As you can see, I can just leave it in terms of u, but what I'll have to do, and it's almost just as much work as plugging the x's back in sometimes, but I'm going to have to change my upper and lower limits of integration to fit in with my u substitution. Okay. Proof of this is in the book. It's pretty short and sweet. I'm going to skip it for now, and let's work that same problem again. So I know the answer is going to be 8 2/3, but let's try to make it so I don't plug that x back in and see if we like it better. All right? We might like the other way better. I don't know. So I'm going to go ahead and rework out this whole problem. So u is going to be just copying what we had earlier, 2x plus 1. And so my du has to be 2 dx. I don't need the 2, so I divided it off. Right there. I want to stop right there for just a second because now my goal is to rewrite my integral. Okay? If I'm rewriting my integral and I don't want to come back to the x's at all right, so if I want to leave it with the 1/2 Let me change all this to red so you can kind of see the new part of it. The 1/2 and the du, that takes place of the dx. Now, I'm not going back to the x's at all. And so I have the square root of u right here, which is still going to integrate the same way. So if I'm not going back to the x's, I can't plug in 0 and 4 because that's what it was in terms of x. I need to get it in terms of u. So in order to get it in terms of u, what I'm going to do is I'm going to take, that just happened. I'm going to take this 0 right here and plug it in for x. If I plug 0 in for x, I get u equals 2 times 0 plus 1. My new lower limit of integration is 1. I'm going to do the same thing for this 4. I'm going to take this 4 and plug it in for x. That's going to give me my new upper limit of integration, which is 9. Okay, a little bit of extra work right here, but in my book, it's worth it. I don't think it's going to be too bad. And so, I'm using red over here, so let's go 1/2, and then I can go ahead and integrate the square root of u. It's still going to be the 2/3 u to the 3/2. But now I get to go from 1 to 9. I don't have to worry about the x's coming back in. So I traded this little bit of work right here for me not having to put the x's back in. And so I'm going to clean this up real quick. 2's cancel still. I got 1/3 u to the 3/2 evaluated from 1 to 9. And whenever I plug in 9 in for this, it comes out a little bit better. So I got, when I plug in 9 to the 3/2, this is square root of 9, 3, 27. I still get the 9. If I plug 1 in for u, I get 1/3. I still got my 9 minus 1/3, which is 8 2/3, which is still the area underneath this curve. That way might have been just seemed so backwards to you, and that's perfectly fine. You don't have to worry about working it that way. You can work it like we did the previous one. Okay. Usually my classes are half and half. Some years they really like to not bring the x's back, like we did in this problem. Other years they say, I don't understand how you changed these upper and lower limits. So I'm just going to ignore all that and work it like we have been. And that's fine as well. So this is normally when I ask my classes, hey, which way did you like better? And they say, oh, yeah, I did it whichever way. I don't get that opportunity this time. So, yeah, let's just work it the new way where we plug in the x's again, all right? Or don't plug in the x's. So I'm looking at what's inside my function. It's definitely that's what's in parentheses right there. Okay? And so if I take the derivative of both sides, I see I don't need that -5, so I'm going to pull that out in front. Okay? And again, just on this one, I'm going to plan on not going back to the x's. Okay? I'm just going to work it where I change my upper and lower limits. So if I do that, I'm going to need to plug the 1 in for this x. Whenever I plug the 1 in for that x, I'm just going to do some math in my head right here. 3 minus 5, that's going to bring it to a -2. Okay, when I plug in the 2 in for this x right here, that's going to be my new upper limit. That's just 3 minus 7. I'm sorry, 3 minus 10 gives me -7. Now, if it bothers you that the smaller number is on top of this limit, we can remedy that. All right, we can change this to a positive 1/5 and then switch these two. It doesn't really bother me, so I'm just going to leave it as it is. So I got the -1/5. If I integrate this, let's see, that's just u to the -2, right? And so if I raise the exponent by 1, that's u to the negative first, put it over the new exponent, -1, that's going to give me -1 over u. Evaluate it from -2 to -7. I like to go ahead and combine these. It would be pretty easy to plug it in right here, but I want to go ahead and get to the answer. So 1 times 1 is 1, negative times negative is positive, 5 times u is 5u. And so I think that this is a little bit easier to plug into. And so, again, plug in your upper limit first. Whatever's on top gets plugged in first. That's going to be negative 1 over 35. And then plug in whatever's on bottom next. All right, so that would be, plus, let me go and do the minus negative. Minus a negative 1/10. And so, common denominators, put in your calculator, whatever you need to do. I got the answer to be 1/14. Get something different, let me know. So we have this u substitution. We can plug it in. You can bring the x's back in. You play with this one and see which way works best for you. So hit pause on the video, make the video a little bit shorter as well, and then I'll work it, and we'll meet back up. All right, I got 1/2 on it. All right. I tricked you a little bit. The u is going to equal the natural log of x. I did a little bit of foreshadowing in my head, and I saw where if I let u equal the natural log of x, when I take the derivative of it, that's going to get rid of my 1 over x. And so cleaned up really nicely over here. Now, there's a couple shortcuts. If you catch these shortcuts, they can cut out some of your work. Okay? If you don't catch the shortcuts, you can work it like we did in the first 30 minutes of this video, and you're going to get all the same answers as the people that use the shortcuts. But we can use symmetry to help us. So if we have that f is a continuous function from, say, negative a to positive a, all right? And first off, let's suppose that f is even. If I am lucky enough to be taking the integral from negative a to positive a of a function, so these two numbers have to match, they just have to be additive inverses of each other, then what I can do is I can just go from 0 to a of my function and double it. Now you're saying, well, what kind of craziness is that? I don't know, let's just look at a function. So suppose I just have a parabola. What I am arguing is that if I'm going from negative a to positive a, finding the area underneath that curve, that this area between those blue lines is the same as if I just found the area from 0 to a and multiplied it by 2. That's all that this is saying right here. Okay. Not much of a shortcut, I know, but hey, if you see it, it might help you a little bit. But this other one's even more of a shortcut. So again, suppose that, I'm going to bring it down here so I don't run into myself. Suppose that I am blessed enough to have it go from negative a to positive a of a function. Remember, this function is going to be odd, so it's going to be symmetric about the origin. My 5th grade son was doing some work on IXL last night, and he was asking me about symmetry about the origin. And so, anyway, hopefully he'll be ready for this in a couple of years. Anyway, if I was to take that derivative, nothing fancy. It's going to be 0 every time. Has to be. Has to be. Think about your favorite odd function. A lot of people say a snake on a plane. If I am finding the area between negative a and positive a, I am willing to bet that there's just as much area down here that I'm going to call a negative area as there is area up here that I'm going to call a positive. In other words, all this positive area is going to get canceled out by all this negative area, and since it's an odd function, those areas are going to be the same. So it has to cancel out and give you 0. So that's why it works. Let's see if we can find a spot in which we can make it work. You got to be able to recognize it. And again, I could work this problem like I've been doing. No need for a u substitution on this because this is just a polynomial. I can just go straight through and integrate this. But if I do recognize that this is an even function right here, it's symmetric over the y-axis, I can cut out a little bit of work for myself by just doubling the integral from 0 to 2. Remember, we love to plug in 0 in at the end. It makes it go a little bit quicker. So this is just no u substitution on this. This is just going to be a straight up integration. I guess I can get rid of my integral sign since I'm ready to integrate. And so it's going to be 1/7 x to the 7th plus x evaluated from 0 to 2. So I'm going to end up with 2 times, well, if I plug in 2 into that, 2 to the 7th power is 128 over 7. And then plug in 2 right here, it's just going to give me 2. If I plug in 0, it's going to give me 0 and 0. So I'm actually subtracting off 0. I'm going to leave that off, though. And then I put all of this in. I got 284 over 7. That would be the area. And that one's not that much of a shortcut. I'm telling you, I could have went from -2 to 2, got the same answer. I just would have had, I would have had to unfortunately plugged in -2 down here instead of 0. And so just a little bit more work right there just to keep straight. All right, we're getting there. I know. I didn't think this lesson would be that long, but it's turned into it. I'll just go ahead and tell you this one's going to be odd. I don't know how you can tell that it's going to be odd. You can plug it in your graphing calculator and you can see that it's symmetric over the origin. It's a lot to plug in, or you can plug in a negative x. I know that this guy right here is going to be odd. It's looking like what's on bottom is going to be an even function, so it shouldn't change the fact that the whole thing is going to stay an odd function. And so since I recognize that it's an odd, and these guys match up, my answer has to be 0. A lot of work to show on that one. So anyway, that happens in your homework set. You can try to find that and enjoy that shortcut, but if you don't find it, we'll still get 0 at the end. Here's your practice problems. If you have any questions on them, put a big star by them and we will definitely hash them out later. Okay? Hope you guys have a good rest of the day and do some math.